Hello, everyone. My name is Leisha Dulader. I'm a junior double majoring in architecture and sustainable product design and innovation. And I've been working at Dr. Hassan Habib's additive biomanufacturing lab for about a year now. And today I will be presenting you on rheological investigation of pre and post cross-linked hydrogels for 3D bioprinting processes. So let's get started. So this presentation is going to cover the introduction to what is 3D bioprinting and why is it important, some of the rheology and what is shared thinning behavior, the biomaterials that we used for this research and the method of making it, rheological analysis of pre and post cross-linked alginate and CMC at 25 degrees centigrade, which also includes flow curve, thixotrophic test. We are going to look at some of the fabricated scaffolds, those which were pre-cross-linked and post-cross-linked, the conclusion and the future work. What actually is it 3D bioprinting? It is a revolutionary technology that uses a computer-controlled 3D printing discipline to release biomaterials layer upon layer along with high precision positioning of cells. So the way it works is cells or a group of cells are taken from a human body or a host body, is mixed with the hydrogel, and this is what we call the bioink. Using different bioprinting technologies, it is printed. The scaffold is further incubated in a proper culture, and therefore tissues are regenerated. The 3D bio printer itself consists of 3 axes. It works on 3 axes, X, Y, and Z. It has a pressure controller so as to extrude the biomaterial with necessary pressure and whatnot, and it has a platform where these scaffolds are finally landed. Here is a small video of how the 3D bioprinter works. On the right is a model of a leaf that was designed in a 3D modeling software. And the red colored stuff is what we call the biomaterial in this research. So why is 3D bioprinting important? Thousands and hundreds of people are waiting for organs, and most of them not being able to get organs in time. So if 3D bioprinting is ever possible in the future, it's going to be a big breakthrough in regenerative medicine. But apart from that, it is also such a big field that supports manufacturing, bioengineering, and organ research. So what is rheology and why is it important for 3D bioprinting? Rheology is defined as the study of flow of material. And when we talk about rheology, shear thinning behavior of the biomaterial is very important because the biomaterials that we are using right now kind of shows properties like ketchup. When I say ketchup, it is very similar to what the ketchup does. So whenever we try to squeeze ketchup out of the bottle, we put pressure, it reduces its viscosity and it squirts out. But after squirting out, when there is removal of pressure, it retains its shape. This is what we call the shear thinning behavior. And shear thinning behavior is very important at 3 stages of 3D printing. First being the rest, second extrusion, and third the retention. So whenever biomaterials are being extruded from a very tiny nozzle, they experience a certain kind of pressure that allows it to reduce its viscosity and print out really easily. But when they land on the platform, it has to take a shape of a certain body part that we want it to. If we are printing nose, we want it to look like a nose and not like a hand. So it's very important that when it retains its shape, the viscosity goes back to whatever it used to be. We can look at the examples of how the low viscous natural polymers upon the printing looks like, and the high viscous polymer. High viscous polymer give a very good structural integrity and shape fidelity to our biomaterial, and it gives a successful print at the end, more than in comparison to low viscous natural polymers. Here are some of the motivations of our work. while we are printing, one of the main challenges is to make sure that it retains the kind of shape that we want the biomaterials to retain. For that, extra cross linkers like calcium chloride, calcium sulfate, calcium carbonate are used. In this research, we used calcium carbonate, and there are two ways of using them. First being the post-cross linking, and second being the pre-cross linking. Previously, we had done a lot of post-cross linking with 4% of calcium chloride after the printing, but there were some of the shortcomings that it had. One being only the edges of the filaments would be cross-linked, and the middle part would be as fragile as a normally printed scaffold. And it was very, very hard for us to maintain the shape fidelity. So we went ahead into, we were very curious about how the pre-cross linking would look like, and we went ahead and did some of the experiments on that. The materials that we are using right now are sodium alginate, which is a big seaweed extract, and carboxymethyl cellulose, which is also a huge, huge molecule. And the cross-linker that we used is the calcium chloride. The composition that we used, all of the compositions were 8% of solid content, and for preparation, we took 8% of solid content and mixed it with 0.5 and 1% of calcium chloride at the beginning for pre-cross linking, and for post-cross linking, we treated it with 4% of calcium chloride at the end. So some of the printing parameters where for rheological tests, we did flow curve, which usually shows us if the biomaterial is showing the shear thinning behavior or not. And then there is thixotropic test that helps us know the recovery rate of the hydrogels, like how it will recover over time. There's also amplitude sweep test that gives us knowledge about storage modulus and loss modulus, which is solid-like character of the biomaterial and the liquid-like characteristic of the biomaterials. So for we went on, after getting the rheological analysis or data, we went further into printing these scaffolds, and for printing we took about 410 micrometers of nozzle diameter, 8 millimeter per second of print speed, and the pressure varied on the basis of different compositions. Here is the result from the flow curve that we took. We can clearly see that no matter if it was pre-cross link or post-cross link, both all three of the compositions or all three of the process of cross-linking showed shear thinning behavior exactly the way we wanted it to show. Over here is the result from the thixotropic test, and we can see, if we were to look at the far right, the recovery rate in terms of percentage after 120 seconds. Post-cross-linked scaffolds showed way more recovery rate than the pre-cross-linked scaffolds. Here are the fabricated scaffolds. On the left are the pre-cross linked, and we can see how it's like, it looks more sturdy, and it's going to hold the structural integrity and whatnot. But on the right is the post-cross linked scaffold, and we can see they are more fragile, more gel-like in structure, and we're less successful in retaining the kind of shape that we wanted it to retain. So in conclusion, what we can see is that pre-cross linking works way more better than post-cross linking in terms of holding its shape, in terms of retention and its power. But we still have not done a lot of cell work, which is our next plan. And it would be very interesting to see how pre-cross-linked and post-cross-linked hydrogels are going to act with the real human or real living cells. Here are some of the future works that we want to do in the future. We want to definitely look and see into printing multiple layered scaffolds. We also are looking forward to doing some cell encapsulation work. Before ending this research, I would like to thank King State College, New Hampshire Biomed, and New Hampshire INPRI for helping us fund this research and giving us the space and equipments to work with. Thank you so much. And please let me know if you have any questions about this research. Thank you.